Welcome back to AI Unraveled, the strategic intelligence briefing for CTOs and VPs of engineering navigating the production frontier of AI. We're focusing today on the heavy metal sectors, energy and construction. These industries are sitting on petabytes of high-value data, yet they face the ultimate architectural challenge, fusing decades of legacy operational technology with a torrent of real-time, unstructured data coming from drones, thermal cameras, and robotic inspection systems. The data silos are not just annoying, they are a threat to operational safety and compliance. The question isn't whether Gemini or Copilot can reason. The question is, can your data architecture feed it the unified context it needs to deliver prescriptive, auditable answers? We're dedicating this episode to the three-stage blueprint for data fusion, proving how you can leverage edge preprocessing, vector databases, and RAG to break these silos and move from reactive maintenance to prescriptive, governed intelligence. Before we dive in, if you're building in the cloud and on the field, please hit that like and subscribe button now to ensure you receive our weekly technical deep dives. And if your company needs to move beyond generic content to deliver strategic thought leadership like this, tailored exactly to your industry vertical, whether it's fintech, health tech, or manufacturing, we specialize in crafting that message. Reach out to our strategy team for partnership opportunities at info@djamgaytech.com. Let's unravel the architecture of industrial AI. This is Industrial AI Unlocked.
Welcome back to the deep dive. Today, we are strapping in for a pretty intense look at industrial innovation. We're talking about two giants, energy and construction. Now, these are sectors that, well, they move mountains, but historically they've moved kind of slowly on technology adoption.
Yeah, that's definitely been the reputation.
But that era, it seems like it's over. These industries aren't just, dipping their toes into AI. They're actually pioneering a specific, really cutting-edge data architecture. And it seems like it's mandatory for handling things at an industrial scale.
Absolutely. It's a necessity now.
So the core challenge, it seems, isn't just running some fancy new LLM. The real issue, the sort of architectural nightmare, is fusing decades of legacy operational data, the stuff locked in old proprietary systems, with brand new terabytes per day streams of unstructured data. Think autonomous drones, advanced sensors. Our mission today is to unpack the specific blueprint needed to make this industrial AI actually work. We'll focus on how enterprise platforms like Gemini and Copilot are acting as that crucial semantic layer, the bridge across this huge data divide.
And look, this is way more than just a tech update, right? For these industries, the stakes are massive, truly existential. We're talking about managing safety-critical operations, ensuring complex regulatory compliance, and protecting billions, literally billions, in physical asset value.
Wow.
You might have infrastructure that's, say, 50 years old, sitting right next to a state-of-the-art thermal camera on a drone. The goal now is to move beyond just analyzing past failures. That's descriptive AI looking backward. We need to get to unified, reliable, prescriptive recommendations, things an operator in the field can act on like right now.
Instantly.
Instantly. And that means you have to connect every single dot, no matter where that data point came from. Old system, new sensor, doesn't matter.
Okay, let's unpack that. Let's start by really defining this data silo problem, because when we talk industrial data, it's a bit more complicated than just data in two different spreadsheets.
Oh, exactly. We're dealing with fundamentally different kinds of information.
Yeah.
Often they don't even share a common file format, let alone a common language or meaning. So on one side, you've got your operational technology data, OT data.
Right.
This is your highly structured, often very old legacy information. Think readings from SCADA systems. Those are the core industrial control systems running physical pumps, valves, gauges. Some have been operating for decades.
Decades, wow.
Yeah, pressure readings, seismic reports from exploration, historical maintenance schedules, often locked away in systems that are really hard to access.
Okay, so that's one side, the structured historical side. What's the other?
The other side is, well, you called it the Wild West. It's the new data streams.
Okay.
And these are just enormous. Terabytes of unstructured content, high-resolution photos, LiDAR scans creating 3D point clouds, thermal imaging, all captured by autonomous gear like drones inspecting pipelines or construction sites. The sheer volume is staggering.
So here's the fascinating question then, isn't it? How do you possibly get a fine-tuned LLM, let's say an enterprise version of Copilot, to understand both a superstructured, maybe decades-old pipe stress report and the visual drone footage that clearly shows a tiny microfracture, and then synthesize those into one single, reliable, and importantly, auditable output? They just don't speak the same language.
They really don't. And what's so interesting here is that the answer isn't just about getting a bigger AI model. It's all about the pipeline, the architecture we build underneath the model. This architectural shift is what lets these industrial players finally move toward that prescriptive, real-time AI. It worked by breaking down two specific barriers that have, historically held heavy industry back.
Okay, let's focus on those two barriers. What are they?
So first, there's the language barrier. This is huge. It's all that tacit human knowledge, expertise, text and speech buried in decades of technical manuals, repair logs, maybe even handwritten notes engineers scribbled on physical blueprints way back when.
Stuff that was basically inaccessible to computers before.
Exactly. Locked away. Unusable by digital systems at scale. That's barrier one.
And the second barrier.
Barrier two is the sensor barrier. This is all that raw, unstructured, visual, acoustic, thermal data we just talked about. Stuff that no traditional OT system could ever interpret on its own. It's basically just noise.
Until
a modern computer vision model or some other sensor processing AI can actually process it and extract meaning. So the LLM's role then is to act as that unifying semantic layer. It sits strategically between all those different silos, the sensor data, the SCADA system data, the maintenance logs, the human technician, and it performs the necessary translation and, crucially, the reasoning.
Okay, that makes sense. The LLM as the translator and reasoner? But that brings us right back to the architecture. If the LLM is the brain, what's the nervous system connecting everything? Because let's face it, there's a critical practical reality here. You simply cannot afford, financially or logistically, to send, say, 50,000 high-res thermal images from an offshore oil rig to the public cloud every single day.
Nope.
The bandwidth costs alone, the storage, it would be crippling.
Absolutely debilitating. And that constraint, that very real financial and logistical limit, basically dictates a new three-stage blueprint for industrial AI.
Yeah.
We have to process data where it makes the most sense, which usually means as close to the source, as close to the sensor as possible.
Right. So if bandwidth is the big enemy, where do we physically start processing all this raw data?
That brings us to component one, edge preprocessing. This is your first line of defense. It's deployed right there on site.
Like on the actual construction crane or the pipeline inspection drone itself?
Yes, exactly. On the crane, on the rig, maybe in a ruggedized box at a remote substation. It uses specialized hardware think MPUs, neural processing units, or maybe specialized GPUs designed for this. And the goal here is incredibly important. Filter out the noise. Filter out maybe 90% of the irrelevant data before it ever needs to be sent anywhere.
90%. So you're not sending the picture of just clear blue sky or the blurry images from turbulence.
Precisely. It's like having a smart assistant automatically reviewing those 50,000 photos, but only flagging the 3 that actually show something potentially important, like a specific type of dent or a thermal signature that's outside the norm. It filters out the clear sky, the bad lighting, the redundant scans. It just localizes the anomalies. It might mark the exact coordinates of potential rust spot in one image out of thousands.
Wow.
That 90% reduction, that is the absolute game changer for making this economically viable. It tackles the cost and bandwidth problem head on.
Yeah, that makes a huge difference. So once we have that much smaller, high-value, anomaly-only data package, maybe the GPS coordinate, the thermal delta reading, the relevant cropped image snippet, where does that distilled intelligence go next?
Right. So that curated package moves to component 2, the contextual data fabric. Now, this typically lives in a central but often hybrid cloud environment, not necessarily all public cloud. And this is where the real synthesis, the magic of fusion, as you put it, truly happens. It's powered by a critical piece of technology, the vector database.
The vector database. Okay, we hear that term thrown around a lot, but it often sounds pretty abstract. Can you simplify how it actually fuses this old structured OT data with the new unstructured sensor data snippets?
Yeah, let's try. Think of it this way. The vector DB doesn't really care about the original file type. It's designed to convert every piece of information, whether it's a line of text from a 1980 maintenance log, a numeric temperature reading from a live SCADA feed, or the key features extracted from that drone image into a mathematical representation, a coordinate point, or a vector in a high-dimensional space.
Okay, so everything becomes numbers, coordinates.
Sort of. It then stores related coordinate points, related vectors, right next to each other in that space. Even if one came from a 40-year-old database and the other came from a sensor 5 minutes ago, Their proximity in the vector space signifies a contextual relationship.
Let's use our rust spot example again.
Perfect. So the vector representing the visual characteristics of that newly identified rust spot from the drone image. It gets stored mathematically close to the vectors for that specific pipe's age from an asset database, its last scheduled maintenance date from the legacy maintenance system, and maybe its material composition from an inventory database.
Ah, so they're linked now, not just sitting in separate databases.
Exactly. They are mathematically fused and contextually linked within the vector DB.
Which means when you query the system, you're not hitting 3 different isolated databases that probably don't even talk to each other easily.
Correct. You're querying one single, unified, contextualized intelligence asset. That's the goal.
That is a huge leap.
It is. And that naturally leads us to component 3. The LLM is the reasoning engine. The large language model, maybe it's Gemini, maybe it's Copilot, maybe something else sits right at the top, interacting with that contextual data fabric. It accesses that unified knowledge using a technique called retrieval augmented generation, or RAL.
RAL. Okay, another key concept here. So it retrieves relevant data from the vector DB and then it generates the response. But isn't RAG sometimes just seen as a fancy lookup tool? How does it actually perform reasoning to turn that raw fused data into a genuinely prescriptive answer? That seems like more than just lookup.
That's a great question because you're right. Industrial AI demands real reasoning, not just spitting back facts. The RAG mechanism here retrieves not just, say, the visual data snippet of the rust spot because of the vector DB.
Because they're linked.
Exactly. Because they're linked, it pulls all its related context simultaneously. The pipe material specs, the recent pressure history from the SCADA system, the date of the last weld from the maintenance log, all retrieved together. The LLM then applies its broad training, often fine-tuned on industrial scenarios, to synthesize these disparate facts. It models potential failure modes based on that combined evidence. It effectively acts like a highly experienced system integration expert, but at machine speed.
So the field technician, they don't have to mentally juggle information from a dozen different dashboards, trying to connect the visual dot to the maintenance history dot themselves.
Precisely. They skip that tedious error-prone step. They just ask a unified natural language question, like the prescriptive question. Okay, what's the immediate risk of corrosion in Sector 4 today, based on all available data, and what action should I prioritize? The model then queries the fabric via RA, pulls that complete fused context, performs its reasoning, and generates a unified prescriptive answer. Something like, risk assessed as high, based on recent thermal variance delta, age of material T45, and proximity to previous weld failure. Recommendation: deploy NDT weld inspection team within 48 hours. Consider rerouting flow via auxiliary line alpha during inspection.
And crucially, it's auditable. You can trace back why it made that recommendation.
Yes, that's key for compliance and safety. Because it's using RA on specific retrieved data, you can usually see which data points, the thermal image, the maintenance log entry, the pressure spike, led to the conclusion. This 3-stage process edge fabric LLM with RA is really the only practical way we found to achieve intelligence that is both powerful and governed and auditable out in the real world in the field.
Okay, this architecture, it isn't just theory. You're saying it's actually driving massive returns right now. Let's make this concrete. Can we look at a couple of specific case studies? Show how this blueprint works in the real world.
Yeah, absolutely. It's crucial to see it in action. Our first example comes from Skanska, a major player in the construction sector. Their challenge: ensuring the physical structure being built on site actually matched the complex digital design plans in near real time. Mistakes caught late are incredibly expensive to fix.
Right, concrete cures fast.
Exactly. So they're now using integrated drone data photos, LiDAR scans, to create constantly updated digital twins of their active job sites.
Okay, digital twins are powerful on their own, but where does that specific 3-stage fusion architecture we just discussed come into play here?
Great question. The fusion happens when the LLM, sitting on top of their data fabric, is continuously fed 2 crucial streams. First, the unstructured data. Drone-captured progress photos and LiDAR scans, pre-processed at the edge, on or near the site, to highlight key features and changes. Second, the structured data. The building information models, or BIM models. These are the detailed digital blueprints that dictate precisely what should be built, where, and to what tolerance.
So the LLM compares the assets from the drone with the should-be from the BIM.
Precisely. The LLM is trained to constantly compare the real-time site data against the approved BIM plan and automatically identify deviations before the concrete cures or before the next phase builds on a mistake.
So it's not waiting for a project manager to manually sift through thousands of photos and compare them against dense diagrams.
No way. The system effectively turns that raw visual data coming from the edge into structured deviation metrics. Things like alert. Wall 3B foundation appears misaligned by 4 centimeters relative to BIM coordinate XYZ. The LLM in this setup acts almost like an autonomous AI auditor for the project manager. It flags that small misalignment now before it cascades into a $5 million structural rework 6 months down the line.
That is a really powerful example of prescriptive AI preventing huge costs. What about the energy sector? Another example there.
Yep, our second case is Imperial Oil, focusing on pipeline integrity and maintenance. For decades, as you can imagine, pipeline inspection was very costly, often manual, maybe involving helicopters or walking crews, and usually based on fixed schedules, not actual need.
Right. Inspect every pipe every X years, whether it needs it or not.
Exactly. Imperial Oil made the shift to continuous AI-driven inspection by implementing this kind of 3-stage architecture.
Now, given that some energy assets can be incredibly old, 50 years or more, what was the specific breakthrough? How did they make fusion possible between, say, 50-year-old control system data and the very newest AI vision models on drones?
Well, a primary part was definitely establishing a common data ontology, that shared language, that semantic understanding between systems that we talked about earlier. That's foundational. But I think the most powerful insight from their work is the unique feedback loop they managed to establish. They didn't just use the LLM to process the real-time sensor data from the drones.
What else did they do?
They used the LLM to process thousands of their legacy maintenance reports. These are often just, unstructured text documents. Engineers describing past repairs, failures, observations, and sometimes from decades ago.
Wait, hang on. You're saying they used the LLM to read old text-based repair logs?
Yes.
To actually train the modern edge-based computer vision models, the ones analyzing the new drone images.
Absolutely. That's the really clever feedback loop. The LLM extracts decades of historical context from that unstructured text. For instance, it might learn when pipe segment X experienced a specific type of external corrosion failure back in 1995, the maintenance log noted visual characteristic Y and precursor condition Z.
Okay.
That historical text-derived insight is then used to fine-tune the proprietary computer vision model running out there on the MPU at the edge. It essentially tells the edge AI, based on past failures described in text, pay extra close attention if you see this specific kind of rust pattern or thermal anomaly today.
Wow. That is genuine fusion. You're bridging deep historical context trapped in old text files with immediate real-time sensory data interpretation.
That's it. It's using past wisdom to sharpen present perception.
Okay, so let's bring this home. What does all this mean for you, the listener? Maybe you're a leader or an engineer in energy construction or a similar heavy industry. It sounds like the key message is your industrial AI strategy cannot just start with the question, which cool new LLM should we try out?
That's putting the cart before the horse. It has to start further down the stack. The first questions need to be, how do we structurally, architecturally, and technologically fuse our disparate data streams? How do we break down these silos? The model itself, whether it's Gemini, Copilot, Claude, whatever comes next, is only ever going to be as effective as the unified, contextual, reliable data foundation you manage to feed it. Garbage in, garbage out still applies, just at a much larger scale.
So, to quickly summarize this entire architectural shift we've been discussing, success really hinges on deliberately engineering these 3 stages, designed specifically to handle the unique challenges of industrial data, the volume, the variety, the velocity, the legacy constraints. First, edge filtering. Managing that data deluge right at the source, running lightweight, specialized models on-site, maybe on NPUs, to get that crucial, say, 90% data reduction before transmission.
Essential.
Second, the contextual data fabric. Using that vector database technology in a central hub to seamlessly mathematically fuse your legacy OT data, your structured logs, with your pre-processed high-value sensor data snippets from the edge, creating that unified view.
Yep, the fusion core.
Yeah.
And finally, stage 3. The LLM as a reasoning engine, leveraging retrieval augmented generation, RAG, to query that unified fabric, delivering not just information but prescriptive auditable answers that genuinely synthesize decades of historical wisdom with immediate, real-time sensory input.
This whole transformation, it really sounds like it's about achieving a fundamentally new level of operational rigor and intelligence. It's successfully moving beyond just, analyzing data points in isolation. It's turning what were previously decades of scattered, siloed information into a single, cohesive, unified intelligence asset for the entire operation.
That's exactly it. And that is the ultimate value proposition for heavy industry as it navigates the next decade. This transformation isn't just about digitization for digitization's sake. It's about turning latent historical knowledge and real-time observations into proactive, data-driven, safer, and more efficient operational decisions. This three-stage blueprint edge, fabric reasoning engine, it really feels like the architectural key unlocking that future for industrial AI, for industrial output, and for operational excellence.
That concludes our deep dive into industrial AI Unlocked. The core takeaway for your strategy is clear. The LLM is only as effective as the unified data fabric you build beneath it. By prioritizing edge filtering for volume control and the vector database for contextual fusion, you create the necessary architecture for auditable, prescriptive AI outputs in critical industrial environments. Our conversation continues tomorrow when we shift focus to the legal and technical requirements for deploying synthetic data at scale, essential listening for every compliance and data governance leader. Before you go, if this episode has provided valuable technical insights for your next sprint or strategic planning session, please take a moment to rate the show and hit that like and subscribe button. Your support helps us remain the most focused, high-signal podcast in enterprise AI. And a final note for our corporate partners. Are you seeking to establish authority and deliver clear technical value to your enterprise customers? If you're looking for a bespoke podcasting solution, a vertical briefing written and produced specifically for your niche, our team at Dissecting Tech is ready to partner with you. For information on creating a tailored thought leadership channel that speaks directly to VPs and CTOs in your industry, contact us today at info@dissectingtech.com. Thanks for tuning in to AI Unraveled. Until next time, keep building.